Hello everybody, today is December 9 and it's time to open a new problem on LeetCode for our coding advent calendar. Today's problem is about binary tree again, and the solution is very similar to one we had before. Let's check it out. Okay, here is today's problem. Maximum difference between node and ancestor. Giving a root of binary tree, find the maximum value v for which there exist different nodes a and b, where v equal to module a value minus b value, and a is an ancestor of b. A node a is an ancestor of b if either any child of a is equal to b, or any child of A is an ancestor of B. Okay, here is an example. We have a binary tree here, and we need to return the value 7 here, because the maximum difference between node and ancestor is 7. The node here is 1, and its ancestor we are pointing to is the root of the tree is 8, and the difference between 8 and 1 is 7, and you will not find any other pair of nodes in this tree which will give you a better v, maximum v. So it's the biggest v we can get from this tree. And for here, for example, we need to return 3 because, again, by module here a value minus b value, and we will pick this node and this ancestor. Ancestor's value is 0 and node's value is 3. So the difference is 3. By module. 0 minus 3 by module is 3, and we cannot get any better result. Okay, so the number of nodes can be up to 5000, and let's do this. How are we going to solve this problem? The idea is to go down from the root till the leaf level, and for each individual path we are going to collect maximum value of node and minimum value of node. And when we are on a leaf level, we will start folding our recursion calls by calculating difference between max and min. That's how we are going to collect v value, and on each backward step we will pick the maximum v which is calculated. So it will look like this. So first of all, we need to cover corner case. The corner case here is the case when root is null. So if we don't have any node, so if our root is null, we need to return something, and we cannot calculate anything, so we are going to return 0. If root equal to null, return 0. Okay, what next? We need to go down through the tree branches from the root to leaf level and collect two values, max and min. Okay, so for this case we will define a separate function which allows us to pass these values from one level to another one. This is actually a DFS algorithm, because we do this in depth of the tree. So DFS okay, here, and we will call this function from our main function like this. So when we start working, we will initialize our max value and min value by the current value of this node. When we will go deeper, for example here to the left, we need to update the min value to 3. So max will be 8, min will be 3. When we go deeper, min will be 1, max will still be 8. And here we are going to collect this. 8 minus 1 is 7, and we will pass it back. So first we need to update our max and min values. And min. Okay, now we have collected these two values, we updated them, and we are ready to pass them into our binary recursion calls. So we need to call DFS for root left and DFS for root right. And these calls will return actual calculated value, and this actually is going to be it is going to be a result, so it will be a difference between max and min, and in the result we will return maximum of right or left branch results. And the one thing we need to add here is when we reached the bottom of our tree, when we reached the leaf level and we go deeper to the left and to the right, we have nulls as a root. So here, if root equal to null, we are going to return max minus min. Okay, so here we start from 8, go deeper to the left, and we have 3, 8. 8 is the max, 3 is min. We go deeper, we have min 1, max 8, and we calculate 8 minus 1 and toss it back and back and so on. So on each way back we are going to calculate the maximum difference. So if we are considering this part of tree, so it will also go here to the right, and from here we will return 7. From here we are going to return 4, because the max difference in this part will be 8 minus 4. It is 4, so we will pick this one. Okay, so let's run our algorithm. Okay, this node is called root. Okay, both cases are accepted, and let's submit our solution. Okay, done. It is implemented. Let's talk about the complexity. So the time complexity of this algorithm is big O of n, because we are going to visit every node in our tree. And the memory consumption of this algorithm is big O of logarithm n, because logarithm n is the height of this tree, and at some point of time we are going to have we have recursion here, and at some point of time we will have as many recursion stack frames as many nodes we have in a tree in depth. So the height of the tree, and the height of binary tree is logarithm. That's it. This problem can look difficult before we starting solving it, but once we finished, it doesn't look difficult at all. This is the reason why we do the practice and improve our skill. The skill will help us to recognize a similar pattern on a real problem, and our solution will be elegant and efficient. See you tomorrow!